Hello everyone. Today I'm going to explain some other topic regarding optimum design. In first part, we already seen introduction of optimum design, classification of design parameters, and introductory part of Johnson's method for optimization. Now the next part content will be categories of optimum design problems, optimum design for normal specification, in that we will see procedure and numerical. In Johnson method of optimization, we already seen the introduction. Now, in that we already seen what is the preliminary design equation, what is the subsidiary design equation, and what is the limit equation. Now next is categories of optimum design problems. According to Johnson's method of optimum design, any optimum design problem falls under one of the following three categories. First one is the normal specification, second one is redundant specifications, and third one is incompatible specification. We will see one by one what is the difference and what are the types of numericals for fall under the normal specification, redundant specification, and incompatible specifications. Now, first we will see optimum design for normal specifications. In the optimum design of mechanical element, if it is possible to develop the primary design equation to the point where the effect of all subsidiary design equations, limit equations, and specified parameters are included, and unique optimum design can be directly obtained, then it is the case of normal specification. Basically, in short, we have to include all subsidiary equations, limit equations, specified parameters, and we have to develop one primary design equation. Then after solving primary design equation, we will get unique optimum design for the mechanical element. Then if it is possible, it is known as the design for normal specification. In case of normal specification, it is always possible to combine all the subsidiary design equations with the preliminary design equations without eliminating or ignoring a limited or specified parameters. This is the simplest case. Now, the procedure for solving optimum design problems with normal specification is as follows. First of all, list down all the given data which is mentioned in design problem. Second step is identify all design parameters involved in design problems. Next step is decide the basis of optimum design, which is the most significant functional requirement to be maximized or the most significant undesirable effect to be minimized. Most significant undesirable effect to be minimized, like minimization of cost, minimization of weight, and most significant maximization effect, it should be like maximization of power transmission capacity, maximization of strength, etc. Next step is write the primary design equation, that is PDE, which expresses the quantity to be optimized. Here we will get one primary design equation. Next step is write all subsidiary design equation, that is SDE, which express the functional requirement and undesirable effect other than the quantity to be optimized. In subsidiary design equation, the quantity to be optimized, it should not be included. Write Next step is write all the limit equations for the design parameters, which includes functional requirement parameters, material parameters, and geometrical parameters. Next step is classify all design parameters mentioned in primary design equation, secondary design equation, and limit equation on basis of status in design problem, that is specified parameters, limited parameters, and unspecified or unlimited parameters. Next step, which is important, combine all SDE, that is subsidiary design equation, with primary design equation by eliminating only unspecified and unlimited geometric parameter that are common in primary design equation and secondary design equation. Now, what is the meaning of this statement? In primary design equation and in secondary design equation, you have to observe which are the common geometrical parameter which is unspecified and unlimited in design problem. Okay, then combine SDE with PDE. Generally, one unspecified and unlimited parameter gets eliminated from primary design equation for each subsidiary design equation. This equation is called as develop PD, that is develop primary design equation. Write the PDE in terms of a group of functional requirement parameters including undesirable effect, material parameters and geometrical parameters. This is known as final primary design equation. From the final primary design equation, using the material parameter group, select the optimum material. This material parameter group is known as material selection factor and its value will determine the optimum available material. And last step is the optimum values for the eliminated geometrical parameters, that is geometrical parameters which were eliminated from primary design equation are obtained by solving the originally subsidiary design equation and you will get the value of eliminated geometrical parameter. We will see the example. A tensile bar of length 500 mm is subjected to constant tensile force of 3000 Newton if the factor of safety is 2. Design the bar with the objective of minimizing the material cost out of the following material. Material is given plain carbon steel, aluminum alloy, titanium alloy. For these materials, mass density, material cost per unit mass in rupees per kg and yield strength in Newton per mm square is given. This is the circular cross-sectional tensile bar. Observe this numerical. This is the first step and write down the given things from the design numerical. See, before proceeding the numerical, length 500 mm is given, that is the specified parameter. Okay, factor of safety 2 is given, that is also the specified parameter. But if force is given, that is also the specified parameter. Okay, now given things, we will see the abbreviations for this first. Capital CM is material cost for tensile bar in rupees. Small c is the cost per unit mass for the bar material in rupees per kg. Rho is mass density of bar material in kg per meter cube. Capital A is cross sectional area. Capital L is length of the bar. Capital F is tensile force acting on the bar. NF is factor of safety. Sigma T is tensile stress induced in the bar Newton per meter square. And SYT is yield strength of the bar material in Newton per mm square. Now we will see the answer of this numerical. First, primary design equation. See what is the main functional requirement is minimization of the cost of the bar. That is the material cost of the tensile bar. We have to minimize capital CM. So capital CM is the material cost of the tensile bar is given by the equation is equal to cost per unit mass of the bar into mass of the bar. Now cost per unit mass of the bar is a given thing from the material list, that is small c into mass of the bar is rho into A into L. So capital CM is equal to C into rho into A into L in rupees. It is the material cost of the tensile bar which we have to minimize. Next is subsidiary design equation. Subsidiary design equation, I already explained you that is in most of the cases stress equation is the subsidiary design equation. So sigma T is equal to force upon area because cross sectional area A is given circular cross section but it is unspecified. Okay, but force is given 3000 Newton, it is a specified parameter. So sigma T is equal to F upon A is the subsidiary design equation and the limit equation is factor of safety is given. So sigma T it should be less than or equal to S by T divided by factor of safety. Now subsidiary design equation is combined with PD by eliminating the unspecified and unlimited parameter capital A. Observe the first equation, that is the Cm is equal to C into rho into A into L and subsidiary equation sigma T is equal to F upon A. Small c is specified parameter, L is also specified, F is also specified. Okay, but the only one parameter, that is the capital A, is unspecified and unlimited parameter. So remove the capital A and combine the SD with the PD. So Cm is equal to C into rho into F into L divided by sigma T. We already eliminated the capital A and developed the new PD. This is the case of normal specification. All subsidiary equation we can combine with the PD, then it is the case of the normal specification. Combining limit equation with the PD. Now, limit equation is sigma t is equal to SYT upon NF, and put that value and you will get Cm is equal to C into rho into F divided by SYT divided by NF into capital A. Now classify the parameters according to the functional parameters, material parameters and geometrical parameter. So F, NF, that is factor of safety, and L is the functional parameters, while C, rho divided by SYT is the material parameters on which your optimum cost will be dependent. So separate them. So your final equation is, and after putting the value of F, factor of safety and L, Cm is equal to 3000 into C into rho divided by SYT. Now selection of material. We already know the rho, small c, and SYT for the materials: plain carbon steel, alloy steel, aluminum alloy and titanium alloy. Material selection factor C rho divided by SYT we can calculate by putting the all values of material, and from this we can see the plain carbon, for the plain carbon steel the value of C into rho divided by SYT is minimum. So for the minimization of the cost, plain carbon steel is selected. So determination of eliminated parameters. Which is the eliminated parameter? Capital A, which is the eliminated parameter, can be determined by using subsidiary design equation. So substituting the limit value of sigma t in previous equation, that is sigma t is equal to F upon A, also sigma t is equal to SYT upon NF. Equate both equation, you will get A is equal to F into factor of safety divided by SYT. So for the plain carbon steel, which material we have selected, SYT is 400 into 10 raised to 6 in Newton per meter square. So put all the values and you will get capital A is equal to 15 mm square. Now the cross section of the tensile bar is circular. So for the bar of circular cross section, capital A is equal to pi by 4 into d square. So put the value of A, you will get the capital small d, that is the diameter of the tensile bar, it is 4.37 mm. So minimum material cost, finally putting the value of parameter C into rho divided by SYT into 3000 is equal to 1.638 rupees is the material cost, which one is the minimum or optimum from the given material, which one we have to select. So write down in last, plain carbon steel is selected to for optimization of minimum cost, it is 1.638 rupees. Thank you for listening.